Now that we've classified our elements into groups on the periodic table, let's see how to determine the number of valence electrons. And so for this video, we're only talking about the valence electrons for elements in the main groups. So when we talk about the main groups, you're using the 1 through 8 system for classifying groups. So 1, 2, 3, 4, 5, 6, 7, and 8. So we're going to ignore the other way to number the groups, and so therefore we're going to ignore groups 3 through 12 for this video. And so if you're talking about the main groups, the valence electrons are the electrons in the outermost shell, or the outermost energy level. And so let's see if we can figure out how many valence electrons sodium has. So for sodium, all right, if I wanted to write an electron configuration for sodium, I assume you already know how to do these. So you would say it is 1s2, 2s2, 2p6, and that takes you all the way over here to neon, and then that brings you to the third period, or the third energy level, and you have one more electron to worry about, and so that electron would go into a 3s orbital. So the full electron configuration is 1s2, 2s2, 2p6, and 3s1. When I want to figure out how many valence electrons sodium has, right, the number of valence electrons would be equal to the number of electrons in the outermost shell, the outermost energy level. For sodium, sodium has the first energy level, second energy level, and the third energy level. The outermost energy level would of course be the third energy level. So if I see how many electrons sodium has in its outermost energy level, right, it's only 1 this time. So that means that sodium has 1 valence electron. And that's very convenient because sodium is found in group 1. And so we can say that for main groups, if you want to figure out how many valence electrons you have, right, it's just equal to the group number, right? So the group number is equal to the number of valence electrons, and so that makes everything really easy. And so if I wanted to represent a neutral atom of sodium with its 1 valence electron, I could draw sodium here, and I could draw 1 valence electron next to sodium like that. All right, let's go ahead and write the electron configuration for chlorine next. So here's chlorine over here. And so if I wanted to write the electron configuration for chlorine, it would be 1s2, 2s2, 2p6, and once again that takes me all the way to neon. And so now I'm over here in the third energy level, or the third period. I can see that I would fill 3s2, so 3s2, and that puts me into my p orbitals. So how many electrons are in my p orbitals? 1, 2, 3, 4, 5. So I'm in the third energy level, I'm in p orbitals, and I have 5 electrons. And so that would be the electron configuration for chlorine. If I want to figure out how many valence electrons chlorine has, I have to look for the electrons in the outermost shell, or the outermost energy level. So I have, once again, the first energy level, the second energy level, and the third energy level. So I want the total number of electrons in the outermost energy level. So how many electrons are in the third energy level? Well, there's 2 and 5 for a total of 7. So chlorine has 7 valence electrons. And once again, that's very convenient because chlorine is in group 7. And so let's go ahead and draw chlorine with its 7 valence electrons. So here is chlorine, right? So 1, 2, 3, 4, 5, 6, and 7, like that. And so the reason I picked sodium and chlorine is, of course, because sodium and chlorine will react together to form sodium chloride. And let's analyze what happens using our electron configurations. And so sodium is going to lose 1 electron. So a neutral atom of sodium has equal numbers of protons and electrons. But if sodium loses its 1 valence electron, so it's going to lose its 1 valence electron, and I can show its 1 valence electron actually is moving over here to the chlorine. So now when I draw sodium, right, I have to represent it as an ion, a cation. Sodium used to have equal numbers of protons and electrons, but it just lost 1 electron. Therefore, it's left with an unbalanced number of protons, right? So it has 1 more proton than electrons, so it gets a +1 charge. So Na+ is the sodium cation. The sodium cation is stable, and the reason why has to do with the resulting electron configuration, right? So if I look at the resulting electron configuration, right, let me go ahead and use yellow here, it would be 1s2, 2s2, 2p6. And so the electron configuration for the sodium cation is the same as neon, which is a noble gas, and we know that noble gases are generally unreactive. reactive, and that has to do with the fact that their electron configurations are full in their outermost energy level, right? So the sodium cation is stable because it has an electron configuration like that of a noble gas. So for chlorine, right, if we think about how chlorine reacts, chlorine has 7 valence electrons, and let's find it on our periodic table here. So here is chlorine. Chlorine has 7 valence electrons. If chlorine gets 1 more, then chlorine would have an electron configuration like a noble gas, like that of argon. So chlorine will gain an electron here. So let's go ahead and write the new electron configuration if a neutral atom of chlorine picks up an electron, right? The electron would add right in here. So instead of 3p5, right, we would write 3p6. And so the electron configuration for the chloride anion would be 1s2, 2s2, 2p6, 3s2, 3p6. So let me just go ahead and highlight that. 1s2, 2s2, 2p6, 3s2, and then 3p6. Let's go ahead and draw it, right? So we're no longer talking about a neutral chlorine atom here. We're talking about a chloride anion that picked up 1 electron, right? So it took that electron from sodium. So I'm going to show that electron in red has moved over here to chlorine like that. And so chlorine gains an electron. So it used to be overall neutral. It used to have an equal number of positive charges and negative charges, but it just added 1 more electron, right? So that gives chlorine a negative charge, so it's now the chloride anion. And so you have an ionic bond that forms between the sodium cation and the chloride anion here. So the attraction of these opposite charges forms an ionic bond. And so this is an example of a group 1 alkali metal reacting with a halogen, right? So in our video on the periodic table, we talked about elements, right? We talked about these being our alkali metals, and since these alkali metals are all in group 1, they all have 1 valence electron. And we talked about our halogens over here as also being extremely reactive, and the reason they are so reactive is if they add 1 more electron, they have the electron configuration of a noble gas. And so drawing the electron configurations, thinking about valence electrons and thinking about the resulting electron configurations allows you to figure out how these things react. And so that is the reason why we can say that group 1 metals are so reactive, and why we can say that group 7, the halogens, or 17, are so reactive. It's because of this concept of electron configurations and drawing out your valence electrons. And so we could figure out how many valence electrons something else has, right? So let's say we were asked to figure out how many valence electrons oxygen has. Right, so all we would need to do is look at the group number, right? So this would be oxygen is in group 6, and so therefore oxygen has 6 valence electrons. And so if you wanted to represent oxygen with its 6 valence electrons, you could go ahead and draw in 6 valence electrons like that. And so that's a very useful thing to think about, that if you want to find the number of valence electrons, right, think about the group number for main group elements.